The objective of the Tower of Hanoi is to move the entire stacks of disks from one road to another. However, you can only move one disk at a time, and you can only move the disk at the very top. Large disk cannot be placed on top of a small disk. Now I'll show you the animation of the solution to the Tower of Hanoi with 3 disks. You can see you can only move one disk at a time, and you can only move the disk at the very top. And because the larger disk cannot be placed on a smaller disk, the yellow disk is moved to the road at the right hand side instead of the road at the middle, because there's a smaller disk already there. And done. For a more general case, sequence can be used to solve for the minimum number of moves to complete the Tower of Hanoi with n disks. First, let's define Mn be minimum number of moves to complete the Tower of Hanoi with n disks. And now let's look at the cases of n plus 1 disks. First, we have to move n number of disks, which will take Mn moves. Then we'll need one move to move the bottom largest disk to the center. And then another Mn number of moves is required to move the n plates all on top of that one large disk. Therefore, we can say that Mn plus 1 equals to 2Mn plus 1, which means that to move n plus 1 number of disks, we need to double the amount of moves required to move n number of disks and add 1 on it. Now you'll need to solve for this equation to determine Mn in terms of n. Note that M1 equals to 1, as when there is only one disk, only one move is required. However, this sequence may seem difficult to solve. It does not look like a arithmetic nor geometric sequence. That extra plus 1 makes it very ugly. Therefore, the first step is to convert it to a more familiar shape or expression, such as a geometric sequence. This can be done if the expression can be written as Mn plus 1 minus alpha equals to 2 times Mn minus alpha, where alpha is a constant. This step may seem random, but now we can let Tn equals to Mn minus alpha. Therefore, similarly, Tn plus 1 equals to Mn plus 1 minus alpha. Substituted into the original expression, we can get Tn plus 1 equals to 2Tn. Now, this looks more familiar. It's a geometric sequence. So, we can say that Tn equals to 2 to the power of n minus 1 multiplied by T1. Since Tn equals to Mn minus a, or minus alpha, sorry, T1 equals to M1 minus alpha. Substitute these two equations into the equation above, we can get Mn minus alpha equals to 2 to the power of n minus 1 multiplied by M1 minus alpha. Thus, Mn equals to 2 to the power of n minus 1 multiplied by M1 minus alpha plus alpha. We know that m1 is a constant and it is equals to 1 as it is stated here, and alpha is also a constant. So essentially we have already solved for mn in terms of n. However, what is alpha then? Since we know that this expression and these expressions are the same, they should be equivalent. Except we don't know about alpha in the second expression. We can solve for alpha as if it is a simultaneous equation. You can subtract the second equation from the first equation. This will give us alpha equals to 2 alpha plus 1. Hence, alpha equals to -1. Substitute this into the equation we determined previously. We can get mn equals to 2 to the power of n minus 1. Therefore, the minimum number of moves required to complete a Tower of Hanoi with n disks is 2 to the power of the number of disks subtracted by 1. So now we know that mn equals to 2 to the power of n minus 1. If you are not very convinced, you can prove this using mathematical induction as well. When n equals to 1, which is when there's only one disk, it is quite easy to see that you only need one move to move it. Therefore, we can say that m1 equals to 1. So when n equals to 1, the left hand side, that is mn, equals to m1, which is 1. And right hand side equals to 2 to the power of n minus 1. When n is 1, it is 2 minus 1, which is also 1. Left hand side equals to right hand side. So we can say that it is true when n equals to 1. Now we just have to follow the step of induction. We assume it is also true when n equals to k. When there is k disks, we assume it is also doable, where k is obviously a natural number. As it is used to count the number of disks, it has to be a natural number. Now we just have to use this fact to prove that the case is true when n equals to k plus 1. We are ready to prove that and remember in the slides where I showed the case of n plus 1 disks, you have seen the animation that mn plus 1 equals to 2mn plus 1. So the left hand side equals to 2mn plus 1. Sorry, it should be k. And now, using the assumption, left hand side equals to 2 times 2 to the power of k minus 1 plus 1, which is 2k plus 1, 2 to the power of k plus 1 minus 2 plus 1 equals to 2k to the power of k plus 1 subtracted by 1. And this is same as what we see in the right hand side. Left hand side equals to right hand side, thus pk plus 1 is also true. Therefore, by the mathematical induction, if it is true when n equals to 1, and it is also true for n equals to k plus 1 under the assumption that n equals to k is true, but by mathematical induction, you can say that this statement is true. And now we have checked that this formula is true. It is clarified by using mathematical induction. Please like and subscribe if you made it this far, and if you want to see more sequence related videos or any other math topics, feel free to comment down below.